Section 8.6 Alternating Series. This section, we will look at alternating series tests, remainders in alternating series, and absolute and conditional convergence. Let's consider the alternating series in the form of the summation of -1 to the power k plus 1 times ak, where ak is greater than 0. The signs will strictly alternate positive, negative in sign. For example, in this series, summation of -1 to the power k plus 1 divided by k. For k equals 1, the first term would be -1 to the power 1 plus 1 divided by 1, which is the value 1. For k equals 2, -1 to the power 2 plus 1 divided by 2, and we get -1 over 2. One more, for k equals 3, we'll see -1 to the power 3 plus 1 divided by 3, and it turns out to be 1 over 3. As you see, the sign alternates from positive to positive, and so forth, as we see in the series in the form of 1 minus 1 half plus 1 over 3 minus 1 over 4. And the pattern will be in the form of the coefficient 1, -1, 1, and so forth, as a sign switch back and forth. The alternating series will have the factor either in the form of -1 to the power k plus 1 or -1 to the power k, and then it will provide the signs alternate. Other than the divergent test, none of the convergent tests for the series with positive term would apply to alternating series. We call the divergent test the limit of the AK term not equal to 0. Therefore, the series diverges. The alternating series test. For the alternating series in the form of the summation of -1 to the power k plus 1 times ak converges if, number 1, the terms are not increasing. That means the term k plus 1 is less than or equal to the term ak for some k that's greater than some index n. That means it's not necessary to be k starting from the very first term. Starting from some term n and so forth, the ak plus 1 is less than or equal to ak term. And also the limit of the ak as k approaches infinity equals 0. If it doesn't satisfy these two conditions, we can use a divergent test to verify whether it diverges or not. Note that for the positive series, the limit ak as k approaches infinity equals 0 doesn't imply the convergence of the series, but for the alternating series with a non-increasing term, the limit ak does imply convergence of the series. Alternating harmonic series. The harmonic series, which in the form of the summation of 1 over k from 1 to infinity, or in the expanded form as 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so forth. The harmonic series is one of the p series form, or the summation of 1 over k to the first power, where p is 1, or the power p is 1, which is less than or equal to 1. Therefore, this p-series diverges. But for the alternating form of this harmonic series, which in the form of the summation of -1 to the power k plus 1 divided by k, is 1 minus 1 half plus 1 over 3 minus 1 over 4. If we rewrite this as -1 to the power k plus 1 multiplied by 1 over k as a term for the alternating harmonic series, the ak is 1 over k, and check the condition of the alternating series test, which number 1 is ak plus 1 less than or equal to ak for some n index of the term. Ak plus 1 is 1 over k plus 1, where ak is 1 over k. So it is true that the 1 over k plus 1 is less than or equal to 1 over k for all k. That means the terms are non-increasing. The first condition is checked. The second condition, we find the limit of the ak as k approaches infinity, or we find the limit of 1 over k as k approaches infinity and we get 0, which satisfy the second condition of alternating series test. Therefore, the alternating harmonic series converges, where the harmonic series diverges. Examples: use the alternating series test to determine whether the following series converge or diverge. Part A, we have summation of negative 1 to the power k plus 1 multiplied by 3 over k squared. We see ak as 3 over k squared. Use the alternating series test. Check the condition number 1, 0 less than ak plus 1 less than or equal to ak for some k. That means we are going to check whether the terms are non-increasing or not. As we see ak equals 3 over k squared, so ak plus 1 is 3 divided by the quantity k plus 1 squared. Put in the inequality form, 3 over k plus 1 to the power second is always less than or equal to 3 over k squared for k greater than or equal to 1. So the first condition of the alternating series test is verified. And then the second condition, check whether the limit of the ak as k approaches infinity equals 0 or not. So we check the limit of the 3 over k squared as k approaches infinity, and we can see this limit approaching to the value 0. So the condition number 2 checked. Therefore, by the alternating series test, this series converges. In this example, we have the summation of the cosine pi k divided by the quantity 2k plus 1 to the third power. The regular or the general alternating series would be in the form of the summation of negative 1 to the power k plus 1 or the power k multiplied by ak. For this problem, we do not see the obvious term as negative 1 to the power k. Let's verify it term by term. For k equals 0, a at 0 equals the cosine at 0 divided by 1 to the third power, which is 1 over 1 or 1. For k equals 1, a at 1 equals cosine pi divided by 3 to the third power. Cosine pi is negative 1, so the term will be negative 1 over 3 to the third power. For k equals 2, the a2 equals cosine of the 2 pi divided by 5 to the third, or cosine 2 pi is 1. Now the sign of the term is positive, and the term is positive 1 over 5 to the third. Let's do one more term. For k equals 3, so a3 equals cosine of 3 pi divided by 7 to the third power, or negative 1 over 7 to the third power. As you make a list, so this will be the series in the form of 1 minus 1 over 3 to the third plus 1 over 5 to the third power minus 1 over 7 to the third power, and so forth. And then we can rewrite it as the general alternating series as the summation negative 1 to the power of some k times 1 over the odd term, which is 2k plus 1 to the third power. And since k starting from 0, the first term is positive, so negative 1 to the k is the appropriate coefficient of this term. And as k equals 1, negative 1 to the first power, the coefficient of the term going to be negative. So this is the alternating series form of this given series. With this, we have the ak as the form 1 over 2k plus 1 to the power 3. Use the alternating series test we have to verify whether the ak plus 1 is less than or equal to ak or not. And this is also true because for ak equals 1 over 2k plus 1 raised to the third power, the ak plus 1 will be in the form of 1 over 2 times k plus 1 raised to the third. And it is true because the denominator is larger than the denominator of the ak term. So number 2, we find the limit of the ak as k approaches infinity, which is the limit of 1 over the quantity 2k plus 1 to the third. As k approaches infinity, we get the limit value is 0. So number 2 checked. Therefore, by the alternating series test, this series converges.